Hello, Mr. Collier here. Today we're going to start our discussion of Chapter 5, which is all about electrons. By the end of this series of notes, you'll understand how the electrons are arranged around the nucleus. But first we need to back up a little bit and talk about the electromagnetic spectrum. I'm going to start and end this set of slides on this particular image, which is a nice encapsulation of the electromagnetic spectrum. It includes information about what the different names of the types of electromagnetic radiation are, what their relative size is, frequency, and some additional information. And hopefully by the time I get done this, a lot of these things make more sense than they do right now. So let's just start by describing what I mean when I say the electromagnetic spectrum. For a long time, scientists believed that light was made up of tiny particles called corpuscles, so like it was matter. However, in the 1600s, researchers observed that light energy also had many characteristics of waves, like amplitude and frequency, things I'll talk more about in a minute. And modern scientists know that all energy is both particles, which they call photons, and waves, and this dual nature is something we'll get more into in these notes. And photons travel in what we call electromagnetic waves. These waves travel at different frequencies, but they all travel at the speed of light. And the electromagnetic spectrum, which is what we're going to be talking about in this lesson, is the range of wave frequencies from low frequencies to high frequencies. So we're going to talk about all the different types of electromagnetic energy in this lesson. To understand electromagnetic energy, you need to understand what a wave is and how it travels. So we're going to look at the parts of a wave right now. You can see in this diagram the things we're going to be talking about are amplitude, height of the wave. We're going to identify crests and troughs, and the wavelength of a wave. To set forth some definitions, the amplitude is defined as the height of the wave, and the higher the wave, the greater the intensity. So for something like a light wave, a higher amplitude is going to make a brighter light. The wavelength, which is represented by the Greek letter lambda, is usually measured in nanometers for electromagnetic waves, and it's measured from crest to crest or from trough to trough. It is literally the length of the wave. The frequency of the wave, which looks like a lowercase v, but is actually another Greek letter, nu, is the number of times the wave passes a fixed point in a certain number of seconds. So we measure it in cycles per second, which is also called hertz. 1 cycle per second is 1 hertz. So you'll notice that these tend to have lots of cycles per seconds. For example, 93.3 as a radio station is 93.3 megahertz. So that's actually 10 to the 6, so that's 93 million cycles every second. So here's a diagram of all those wave characteristics I just defined. Let's take a look. This line that runs through the middle is considered the normal or rest position, and then the wave oscillates from crest to trough, and as it goes from one crest to another, that's defined as one wavelength, but you can also define a wavelength from trough to trough. That's also acceptable. The amplitude of the wave is from the rest position to either a crest or the rest position to a trough. This wave cycles 1, 2, 3 times, and so if we assume that this is 1 second, that would be 3 hertz, 3 cycles in 1 second. So electromagnetic waves can have longer wavelengths or shorter wavelengths, and this is going to affect their frequency because they're all traveling at the speed of light. A longer wavelength is going to have lower energy, and a shorter wavelength will have higher energy. Here is an image representing all the different things on the electromagnetic spectrum, from long wavelengths on the left to short wavelengths on the right. In the middle is the very thin sliver called visible light. That is what you are used to seeing because that is what the human eyes are tuned to. The visible light spectrum goes from red, orange, yellow, green to blue, indigo, and violet, Roy G. Biv. And those colors have varying wavelengths, but they still all exist within this tiny little sliver of the electromagnetic spectrum. Red is the longest wavelength, violet is the shortest. Just below red, we have infrared. Below that, we have microwaves, then radar, and then radio waves are actually the very longest of the electromagnetic waves. All of these waves have low frequency and longer wavelengths. That equates to lower amounts of energy. So we can safely be around things like radio waves and radar. Going the other direction, we've got ultraviolet light, X-rays, and gamma rays. These all have higher frequency and shorter wavelengths, which gives them higher energy. So you might recognize X-rays and gamma rays as things that you don't want to be exposed to in large amounts because they can be dangerous. Just to give you a little bit more information about each of those wavelengths, radio waves include radio and television, and they're very low energy that bounce off lots of different things. So we can bounce them off satellites and transmit radio and television around the world. Microwaves can pass through some materials but are absorbed by others. So for example, in your microwave oven, they can pass through the glass or plastic container that you're using, but they are absorbed by the moisture in the food so that your food cooks, but the glass container doesn't get hot. Infrared, also known as heat waves, are readily absorbed by darker materials, but generally reflected by lighter materials. The sun emits infrared waves, which is what keeps the Earth warm, and it also contributes to our greenhouse effect, which is why we have life on Earth. Visible light waves, as I mentioned, are in the middle. They are the smallest part of the electromagnetic spectrum, but super important because they're the only ones visible to the human eye. The different colors within that category range from red to violet, and those correspond to shorter or longer wavelengths. Most of the sun's energy is emitted as visible light. The sun also emits ultraviolet waves. These are higher frequency, and that's what causes sunburn. X-rays can penetrate muscle and tissue, but they're blocked by bone, which is why we use X-rays in medical and dental photographs. And gamma rays, which are the highest frequency waves, are more powerful than X-rays, so much so that we can use them in radiation therapy to kill cancerous cells. The nice thing is that the atmosphere protects Earth from the ultraviolet and X-ray and gamma rays that come from the sun for the most part. So here again is the slide I promised to end on as well. We've got all the different wavelengths of electromagnetic radiation from radio to gamma rays, the relative size of those different ones related to how their wavelengths are, the frequencies in hertz, that hopefully you understand what that means now, and how well they penetrate the Earth's atmosphere. So a lot of information there. We're going to talk a little bit more about that as we go through understanding electrons even better, but that's a good background for you to have as we discuss the electron.